Welcome, Mike again here, and we're going to talk about, the normal distribution. But before we even do that, we want to talk about continuous random variables and how they differ from discrete random variables, and then eventually we'll get to the normal distribution, the bell-shaped curve. The major distinction between discrete and continuous random variables is that you can list out all the values of a discrete random variable, and you can't for a continuous random variable. The old math definition of continuous is between any two values of a continuous variable, you can always find another value. There's just an infinite number of values. So you can't list out all the values of a continuous random variable. The other weird thing is that for continuous random variables, the probability you equal any one value is zero. This is not true for discrete random variables, but again, is one of the weird things about continuous random variables. Well, to understand why this is true, we go through a very basic argument. If you're rolling a six-sided die, the probability of rolling a 3, of course, would be 1 over 6. Rolling a 20-sided die, and here's a little history of 20-sided die from the Roman empires. The Roman kids were playing D&D. The probability of rolling a 3 for a 20-sided die is 1 over 20. And you get the idea. If it's a 100-sided die that looks like a ball or a sphere, it's going to be 1 over 100. So what's happening to these probabilities? The probabilities are getting smaller and smaller. So the probability of rolling a 3 is getting smaller and smaller, but one of the basic axioms of probability is that if you sum up all the probabilities of the outcomes, they sum to 1. So if you have an infinite number of outcomes, there's no way to assign a small amount to each probability to have it sum to 1. It just won't work. So we throw our hands up and we say, well, it's going to be 0. So the probability x equals 0 for any possible outcome if you're a continuous random variable. So what do we talk about for continuous random variables? We talk about the probability you're inside an interval. We talk about the probability the continuous random variable x is between the values a and b. Now again, this can be written many ways because equality doesn't matter. So you can have equality here, you can take it out, whatever, just because it's a continuous random variable. Examples of continuous random variables, things you measure: stock returns, a person's hat height, the height of sunspots, amount of soda in a 12-ounce can. Usually things you measure are continuous random variables. Continuous random variables are given or represented by what's called a density curve, a probability density function. And it's a continuous curve, and probability is given by the area under the curve. And it's a very special curve. It has to be either positive or 0. And it's normalized, or it's such that the area under the entire curve is 1. To show you the distinction, this is called a probability mass function, or this goes with a discrete random variable, and height is probability. So that's probability. Height is probability if you are a discrete random variable. If you're a continuous random variable, height no longer is probability. We don't really care what height is. It's just the height of the curve. It would help us find the area under the curve, but what we care about for continuous random variables is the area under the curve. So if we want the probability between 5 and 10, it'd be this area under the curve between 5 and 10. So the density curve has several properties that you can read here. The density curve is not the probability x equals x. Remember, that is 0 for any continuous random variable. To find probabilities, we talk about the probability of an interval, and then we have to find the area under the curve between two values. So if we want to find, oh, that was weird, a z, I don't know why it's called a z there. You want to literally find the area under the curve. You want to find the probability x is between 5 and 10. You have to find the area under the curve between 5 and 10. Usually this involves what's called integration, which is from calculus. We don't assume anyone knows integration or remembers integration. So we actually use continuous random variables where it's very easy to find the area under the curve. Finally, we have what's called the cumulative distribution function, which will actually be pretty useful. And this is just the probability you're less than or equal to some value. We call this the CDF function, the cumulative distribution function. It's the integral from minus infinity to x of f of x dx if you're in the math, but simply it's just the cumulative probability that you're less than or equal to some value. Now this is the key formula for continuous random variables. The probability of an interval is going to be f of b minus f of a. This is a really key formula to know for continuous random variables. And why is that true? Well, let's say we want the area between 4 and 6. We're going to take f of 6. That's everything from 6 all the way to the left, minus f of 4, which is everything from 4 all the way to the left. And that'll give us the area between 4 and 6. That's a very useful formula to know. For completeness, the mean of a continuous random variable. For discrete random variable, you have a sum. For a continuous random variable, you have an integral. And the variance, again, we would sum. Here we have an integral. They're given for completeness. We don't assume calculus knowledge. In case anyone was wondering, continuous random variables require a lot of calculus knowledge. One of the simplest continuous random variables, just to have a feel for playing with one, is called the uniform distribution. And this is a distribution where you take any value in the interval a to b. So you can take any value in the interval a to b. Now, because it's a uniform random variable, the area under this curve has to be 1. So the height is b minus a. Why is the height b minus a? Because the area has to equal 1. And the area of a rectangle is height times length. The general characteristics for uniform, well, the density is given by this. Mathematically, you can go to Wiki and find this. The mean is given by this formula, and the variance is given by that formula. Not insanely hard to show, but not fun to show, and just good to know the final results. Now, it's used uniform. The amount of gasoline sold daily at a service station is uniform distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. Find the probability that sales will fall between 2,500 and 3,000. What's the probability that sales will be at least 4,000? What's the probability that the station will sell exactly 2,500? We can do the last one first. So what's the probability x equals 2,500? Sounds bizarre because you think, yeah, they could sell 2,500, but if you assume it's a continuous random variable, you have to say that's 0. There's no way you can sell exactly 2,500. So what's the probability you sell between, the random variable is on the interval 2,000 to 5,000, so it looks like this. The height's got to be 1 over that. So we know what the density looks like. What's the probability the station will sell exactly 2,500? We're doing the last one first, just to show you via math. It's literally going to be height times length, and the length is 0, so you're going to get 0. And so it's going to be 2,500 minus 2,500 times 1 over 300. This is length, this is height, and you get 0. What's the probability that daily sales will fall between 2,500 and 3,000? Again, you're just finding the area under the curve. You get this. What's the probability the service station will sell at least 4,000 gallons? Area under the curve, and you get that. So the uniform is very easy to work with, insanely easy, but good to play with. Always good to draw a picture to understand what the uniform is. The most common continuous random variable, though, is called the normal distribution. It has equivalent names. It's also called the Gaussian distribution. Albert Gauss, who did a lot of work on it, called the bell-shaped curve because it looks like a bell shape. They're all sort of equivalent names for this. We have a graphical feel for this. Weights and heights and stock returns all seem to follow the normal curve. Not exactly sure why, but they do. And it shows up a lot in nature. So let's figure out what this is. The normal curve, the shape of it is defined by 2 parameters called mu and sigma, the mean and standard deviation. And you might be able to guess from this slide, mu tells me where the middle of the curve is. Sigma tells me how spread out it is. Sigma actually tells me 2 things, and they're related to each other. It tells me how spread out it is, but also how tall it is. Because if sigma gets wider, if sigma goes up, the curve gets wider, the area under the curve has to be 1. So if the curve gets wider, the height goes down. And as sigma gets smaller, the curve gets narrower, but height still has to be 1. The area still has to be 1. So height goes up. We use notation x is. This says x is a normal centered at mu with standard deviation given by sigma. Nice symmetry on this. And there are 2 commands in R. There's pnorm and dnorm, and you'll never use dnorm. Dnorm gives you the height. That's not this, because that's always 0. It's just if you're going to print out the curve, maybe you use dnorm. But by and large, we're always going to use pnorm. That's the cumulative probability. It's the probability I'm less than or equal to some value. So if we want to find normal probabilities, we want to find probabilities between A and B. We use the computer, or we can actually use tables for that too, as we'll show in a minute. So tires have a tread life of average 35,000 miles and a standard deviation of 4,000 miles. What proportion of tires, or what's the probability a tire lasts more than 38,000 miles? We want to find the area from 38 here all the way to the right. We're doing it online with an online calculator. But it's simply 1 minus p norm. P norm would give you the area to the left. We want the area to the right. So it would be 1 minus p norm. What proportion of tires have tread lives less than 35,000 miles? You don't even need a computer for this. The curve is centered at 35,000. Half the area is to the left of 35,000, and then half the area would be to the right of 35,000. What proportion have treasure lives between 30,000 and 38,000? Here we're going to do that trick where it's f of 38,000, 1, 2, 3, minus f of 30,000. And then what's left over will be the area you want. And here we do this in R, the 38,000, the 30,000, and you get the probability. This is easy. It absolutely is. What if you didn't have a computer? Ooh, that wouldn't be so easy, but we'll show you how to do it if you didn't have a computer. Many years ago, it wasn't Albert Einstein. He was working at Meineke at the time, but many years ago, someone realized you can go from X to Z as follows. What's Z? Well, let's show you in a minute. If you take a Z-score, you subtract off the mean, you divide by standard deviation, you can go from any X to what's called a standard normal. So if a normal curve has mean 0 and standard deviation 1, it's called a standard normal curve. So what? This is nice. You can go from any X to a standard normal. Well, in the 50s, someone tabulated the area under the curve for the standard normal, which is something they did with basic electronic calculators. And they found the area under the curve for a standard normal. And they made them in tables. And we'll put a link to a table on the website. And this gives you the area to the left for a standard normal. And the way you read this is the first digit, so 0.5. Let's go 0.65, show you. Here's 0.6, 0.6, 0.61, 0.62, 0.63, 0.64. That's 0.65. So the area to the left of 0.65 is 0.7422. You can see here the area to the left of 0 is 0.5. Because the thing is centered at 0, half is to the left of 0, half is to the right of 0. So you have what are called standard normal tables, and they tabulate areas to the left. So how do we use a standard normal table? You use standardization. You may recall from a long time ago that if you have an inequality and you do the exact same thing to all sides of the inequality stands. What does that mean? Well, if we want the probability x is between A and B, we z-score everything in sight, and it becomes equivalent to a probability statement about z. So for the normal, you can easily make any probability statement about x a probability statement about z. So as an example, a plumbing company has found that the length of time in minutes from installing a bathtub is normally distributed with a mean 160 minutes and standard deviation 25 minutes. What percent of the bathtubs take longer than 185 minutes to be installed? We have the probability x, a question about x, we use z-score, becomes a question about z. So a question about x becomes a question about z. Now the table gives us the area to the left of z. Do we panic? So over here, 8413 is what we want. Do we panic? We always panic, but then we recover. We want the area to the right. So probability z is bigger than 1 equals 1 minus the probability z is less than 1. Z is less than 1 equals 1 minus 0.8413. If we look here, we get 1587, which is this, 0.1587 right here. Just checking our work on the computer, and we get the exact same answer. What's the probability it'll take between 110 and 175 minutes to install? We want to find this probability. It's a probability statement about x. You z-score everything in sight. It becomes a probability statement about z. And then you can easily use your z-table, and again, you would do f of 0.6 here, minus f of minus 2, which you find from the z-table. How do we find this using our z-table? I just did it on the previous slide. I should read ahead. You find f of 0.6 minus f of minus 2, and then you're good to go. Z's and normals are really nice. This is where the empirical rule comes from. 68% of the areas within 1 standard deviation of the mean, 95% of the areas within 2 standard deviations of the mean, and essentially almost the entire curve is within 3 standard deviations of the mean. It goes on forever, but essentially everything's within 3 standard deviations of the mean. Finally, there's something called reverse lookup, where you have a probability and you want to find a value. So we're looking at how long light bulbs last, and they want to be sure that 98% of all light bulbs last longer than the advertised figure. So what would we put down here to say, oh yeah, we're 98% sure light bulbs last 10 hours or more. Like, we want to figure out this lower bound. And you do that via what's called the Q-norm function. So the Q-norm function, you give it Q, and it gives you X, such that the probability or less than X is Q. That's confusing. But you want to find X so that the area to the left is whatever you specify. So here we're asking, what is the value of X such that the area to the left of X is 0.02, 2%, and it turns out to be 4689. So we call that reverse lookup because normally you have a value you want to find a probability. We're reversing that. Now we have a probability we want to find a value. So if you're at 4690, 98% of the area is to the right of you, 2% of the area is to the left of you. So things you want to know about the normal is know the difference between discrete and continuous random variables. Uniform is just a simple example of what a continuous random variable looks like. You know your normal distribution, you know what z-scores are. It's a way to standardize and use a table, a accumulated table of probabilities for the normal, using the normal 0, 1 table goes with z-scores, and you know how to do q-norm for reverse lookup. Hope this was helpful, and look forward to seeing you in class. Thank you.